In this class, we will discuss internal conversion. Internal conversion is an electromagnetic process that competes with gamma emission. For an even nucleus with both a higher excited state and ground state, both has zero value for nuclear spin or total angular momentum of nucleus. That means II and IF both are having value 0. There is no change in the L value, that is L is equal to 0. And no gamma transition with L is equal to 0 is possible. The minimum value is L is equal to 1, which is known as the dipole character, and L is equal to 0 is the monopole character, which is not possible. That we have already mentioned in the angular momentum and parity selection rules. So, there we have mentioned that in such a transition, always this internal conversion is preferred. So, in this case, the electromagnetic multipole fields of the nucleus do not result in the emission of a photon. Instead, the fields interact with the atomic electrons and cause one of the electrons to emit from the atom. In contrast to beta decay, the electron is not created in the decay process, but rather is a previously existing electron in an atomic orbit. This is one of the difference between your beta decay and internal conversion. In beta decay, an electron or positron is created by the transfer of a neutron to proton or from a proton to neutron in the nucleus, and it has the nuclear origin. So, before the decay process, that electron was not present. But here, you have already an electron which is existing in one of the shells of the atom, and that electron is emitted with the decay energy. And the next thing, this is not a two-step process in which a photon is first emitted by the nucleus and then knocks loose an orbiting electron by a process analogous to the photoelectric effect. Such a process would have a negligibly small probability to occur. So, that means this is the case, an example. So, you have a beta emission here. So, your daughter nucleus is at an excited stage and it can release the difference between energy of the excited state and ground stage by a gamma emission. But sometimes this energy, actually in this figure itself you can see that that energy is directly given there. That is an internal process and no photon or gamma is emitted from the nucleus. So, like a gamma is coming from here to this electron, and by absorbing that, electron is emitted. Actually, that is the case. A photon is directly given to an electron, say this electron, and it is emitted. That is happening in your photoelectric effect. Actually, photon is entering into the atom. But here, no photon or no energy transfer is directly you can see here, but internally this energy is given to K and that K is emitted. So, this is your process of internal conversion. And the transition energy delta E, actually delta E is the energy difference between the excited state and the ground state. appears in this case as the kinetic energy TE of the emitted electrons, where it is less than the binding energy B that must be supplied to knock the electron loose from its atomic shell. So that from this delta E, a portion B is used. It is the binding energy of the electron. So the kinetic energy of electrons will be delta E minus B. That is clear. Because the electron binding energy varies with the atomic orbital. You can see that for the K shell, the binding energy is maximum. So it is emitted with the minimum kinetic energy. For a given transition delta E, there will be internal conversion electrons emitted with differing energy that is emitted from different orbits. The observed electron spectrum from a source with a single gamma emission thus consists of a number of individual components. These are discrete components and not at all continuous like the electrons emitted in beta T. So there will be a particular energy for K and another one for L, and there will be no energy between this K and L. So it is a discrete one. Most radioactive sources will emit both beta decay and internal conversion electrons. Just we have seen this example. This is a beta decay, and after that beta decay, internal conversion is getting. And you just neglect these peaks here. So this is the form of your energy spectrum of beta decay. So your beta decay or electrons have a continuous energy, and it is relatively easy to pick out the discrete conversion electron peaks riding on the continuous beta spectrum. So this peak denotes your internal conversion. So internal conversion, you are a particular emitted with a particular, this may be from K for example, this with a discrete energy, and L, etc. And you can see that it has only a discrete energy. If you are not, if you have no beta, you will be getting only this discrete one. So they are mixed with, those electrons are mixed with your beta decay electrons. That is why you are getting a combined structure like this, and you are saying that they are riding on the continuous beta spectrum. The internal conversion process has a threshold energy equal to electron binding energy in a particular shell. So no electrons cannot, that means internal conversion electrons cannot be emitted if they are getting an energy which is less than the binding energy. The conversion electrons are labeled according to the electronic shells from which they come. For example, K, L, M and so on, corresponding to principal atomic quantum numbers. As you know, it is 1, 2, 3. If we observe at very high resolution, we can even see the substructure corresponding to individual electrons in the shell. For example, the L, that means N is equal to 2 shell, has the atomic orbitals S, P, 2s half, 2p half and 2p 3 by 2. So electrons originating from these shells are called respectively as L first, L second and L third conversion electrons. This is known to us. Your L shell can have both S electrons and P electrons, and this P electrons can have angular momentum values half and 3 by 2. So from S you have L first, this is L second, and this is L third. And this is the structure. On a high resolution, you can separately see L1, L2, and L3, L3, first, second, and third. Following the conversion process, the atom is left with a vacancy in one of the electronic shells. This vacancy is filled very rapidly by electrons from higher shells, and thus we observe characteristic X-ray emission accompanying the conversion electrons. Such case we have already discussed in our radiation physics topic. For this reason, when we study the gamma emission from a radioactive source, we usually find X-rays near the low energy end of the spectrum. That means when, in this case, when an electron is, that means a K-shell internal conversion is taking place. So there is a vacancy in K-shell. So an electron from L, M, N, etc. can jump to the vacancy, or they can occupy the vacancy in K-shell. And that difference in energy is emitted as X-rays. So it is the characteristic of a particular atom. That means the difference between energy levels is a characteristic of a particular element. That is why you are calling it as the characteristic X-rays. And normally this energy will be much less than the energy of the emitted gamma. That is why you are saying that when we study the gamma emission from a radioactive source, we usually find the X-rays near the low energy end of the spectrum. Means with the gamma, this internal conversion is competing with your gamma emission. So there is a small fraction of internal conversion is always there with the gamma. One feature that is immediately apparent in the varying intensities of the conversion electrons from the decay. That means varying intensities of conversion electrons is one of the apparent thing that you can you can see. This variation depends on the multipole character of the radiation field. Measuring the relative probabilities of conversion electron emission is one of the primary ways to determine multipole characters. That means if a particular multipole radiation is not possible, the corresponding emission will be, that means in that case more internal conversion will be possible. And if a particular multipole character radiation is more preferred, in that case internal conversion will be less. In some cases, internal conversion is heavily favored over gamma emission. In others, it may be completely negligible compared with the gamma emission. So it is necessary to correct for internal conversion when calculating the probability of gamma emission. That is, if we know the half-life of a particular nuclear level, then the total decay probability lambda t, that normally you are writing as 0.693 by t half, has two components, one lambda gamma arising from gamma emission and another lambda e arising from internal conversion. So you are writing lambda t as lambda gamma plus lambda e. The level decays more rapidly through the combined process than it would if we considered gamma emission alone. So it is convenient to define the internal conversion coefficient alpha as lambda e by lambda gamma. So the internal conversion coefficient alpha is lambda e by, means it is the ratio of the decay constants of internal conversion and gamma emission. That is, alpha gives the probability of electron emission relative to gamma emission and ranges from very small value or nearly zero to very large. The total decay probability then becomes, that means we have written as lambda t is lambda gamma plus lambda e, and lambda e by lambda gamma you have written as alpha. So lambda e is alpha lambda gamma. So it is lambda gamma plus alpha lambda gamma. You can take this lambda gamma as a common factor. So it is lambda t is lambda gamma into 1 plus alpha. And let this lambda t represent the total internal conversion coefficient. We define partial coefficients representing the individual atomic shells as lambda t is lambda gamma plus lambda, actually this is lambda e, and it is lambda e of k, lambda e of l, lambda e of m, etc. And also you can write this as this lambda e by lambda e of k by lambda gamma you can write as alpha k. So similar to this, it will be lambda gamma of 1 plus alpha k plus alpha l plus alpha m plus etc. Thus, you can write this alpha as a combination of alpha k, alpha l, alpha m sums. Considering the subshells, we would break these down further, such as your alpha L can be written as alpha L first, alpha L second plus alpha L third, and similarly for other shells. The calculation of internal conversion coefficients is a difficult process. Since internal conversion process is electromagnetic in origin, the matrix element that governs the process is quite similar to that of gamma. That is a comparison. Your gamma decay is electromagnetic in nature, so this is also electromagnetic in nature. So the same electromagnetic multipole operator that we have written as m of sigma L governs both the gamma emission and the internal conversion. That means you can write the decay, the probability or decay constant of lambda gamma sigma L proportional to the multipole operator or the matrix element as mfi sigma L square and lambda e with the same multipole operator. The internal conversion coefficient alpha, that means the ratio of lambda e and lambda gamma, is independent of the details of nuclear structure. The coefficient alpha will depend on the atomic number of the atom in which the process occurs and on the energy of the transition and its multipolarity. So indirectly you can say that it depends on that means due to this multipolarity, it depends on the nuclear structure. So a non-relativistic calculation gives the following results for electric and magnetic multipoles conversion coefficient. Your lambda EL, this is the case for your internal conversion. Lambda EL you can write as Z cube by N cube into L by L plus 1 E squared by 4 pi epsilon 0 H cross C raised to 4 2 M E C square divided by E L plus 5 by 2. The terms are known to you. This Z is the atomic number and it is the atomic number of the daughter nucleus, and N is the principal quantum number of the bound electron wave function. That means from where your electron is emitted. The factor Z by N cube comes from the conversion rate, and this quantity is normally written as 1 by 137 and is a fine structure constant. This MEC square is the rest mass energy of your electron, E is the energy of gamma decay, etc. And for the magnetic dipole, you are writing it as Z cube by N cube, E square by 4 pi epsilon 0 H cross C 2 me c square by E L plus 3 by 2, where this fine structure is absent here. And of course, here you have 3 by 2 and here it was 5 by 2. So, our expression were here. And based on this expression, we can have some conclusions. The approximate expressions illustrate a number of features of the conversion coefficients. They increase as Z cube. Z cube is in the numerator. You can directly see. So, alpha is lambda E by lambda gamma. So, when alpha increases, lambda E increases. So, the conversion process is more important for heavy nuclei than for light nuclei. The conversion coefficient decreases rapidly with increasing transition energy. That means E is in the denominator. So, when E is more, this is small. The conversion coefficients increase rapidly as the multipole order increases. So, this is almost L by L plus 1 is almost the ratio as 1. But here you can see when L increases, this quantity increases. So, when multipole order increases, you can see that electron emission may be far more probable than gamma emission. So, like suppose you have the L as 4, 5, 6, etc. This will be increasing. So, in that case, multipole gamma emission is very less compared to internal conversion. The conversion coefficients for higher atomic shells, that means n greater than 1, here you have that, decrease like 1 by n cube. Thus, for a given transition, we must roughly expect alpha k by alpha L, all things same. Here for k it is 1 and for L it is 2. So, 2 cube is h. So, alpha k by alpha L is h. Many experimental values of alpha k by alpha L fall in the range of nearly 3 to 6. So, even in this case, our estimate serves as well. That means this approximation is always almost good. That is the proof, or that is the estimate or that is the inference we are getting this result. We therefore expect relatively large K-shell conversion coefficients for low energy, high multipolarity transitions in heavy nuclei with smaller values in other cases. That means conversion coefficients. We have K-shell conversion coefficients expect. That means your n small. Low energy must be also small, and high multipolarity L in our equation, and also Z should be large. That means K-shell conversion coefficients for low energy, high multipolarity transitions in heavy nuclei, and with the smaller values in other cases. That means higher atomic shells other than LK higher values, higher transition energy E large, lighter nuclei, that means Z low, and also lower multipoles. So, this condition is not preferred by internal conversion. The coefficients differ considerably for EL and ML transitions. Thus, measurement of alpha allows us to determine the relative parities of nuclear states. There is one other application for which internal conversion is an essential tool. The internal conversion or E0 transition, you can call it as it is for L is equal to 0 thing, is particularly important in decays from 0 plus initial state to 0 plus final state. The 0 is the nuclear spin or angular momentum of nucleus, and this plus sign shows its parity, that means even parity, which cannot occur by any other direct process. We can regard the nucleus in this case as a spherically symmetric ball of charge. That means we have discussed that only for a spherical distribution you have electric monopole. That means we can regard it as a single charge. So in that case, electron is nearly spherical in its ground state and in the excited state. So you can, if you are getting the E0 transition, clearly you can say that that particular nucleus is spherical in nature. And that's all. Thank you.